Today we're going to take a quick peek at Newton's third law of motion. Some might say his finest law. Some might not. But because there's never a bad time for a little bit of Latin, we have it here in its original Latin form. I'll allow you to read that at your leisure. But in its abbreviated state, and how you may have learned it at one point in your past, Newton's third law says for every action, there is an equal and opposite reaction. But what does that actually mean? In a much more physicsy way, it means that forces come in pairs. Whenever one object exerts a force on a second object, that second object exerts a force back on the first object that is equal in magnitude but opposite in direction. So, important pieces here. Forces always come in pairs. And let's actually put that in there. Always. Okay? You won't ever have just a single force. There'll always be two forces involved. We call them third law force pairs. And those forces are always equal in magnitude and opposite in direction. So let's take a look at a couple examples of this. We know that the Earth pulls on the moon, right? It exerts a gravitational force on the moon, which is what keeps it in orbit. If you didn't know that, now you do. But does the Earth also pull on the moon? And if so, which pull is stronger? So this question is kind of like saying, what's a greater distance? New York to San Francisco or San Francisco to New York? The distances are the same in both directions. It's just a matter of what direction you're going. And it's the exact same with our force pairs. Both the Earth and the moon pull on each other with exactly the same magnitude of force, but they're in opposite directions. Now, when we get to the second law and we start talking about force and its impact on masses, we'll see how we have some different situations based on equal forces but different size masses. But for right now, it's enough to know or enough to say that those forces are equal and opposite. Another great example of Newton's third law is standing on a floor. And in lieu of a picture for this one, I'm going to draw a picture. So here's you. This is you. And you are happy because you're in physics class. And you're standing on the floor in your classroom. And you have a cap on, maybe. So, you have a force pulling you down, right? So let's talk about some of the forces involved here. And we'll draw a free body diagram. So if this is you, you have the force of gravity pulling you down. You have the normal force of the floor pushing you up. In this case, Fn equals Fg, and so you're in equilibrium, and so you have a constant velocity, things that we've talked about, right? But these are not force pairs. Not force pairs. Let's start with our normal force. So let's focus on our normal force for a moment. Okay? So our normal force, if we think about our description of forces, the normal force, let's see, the floor is exerting a normal force upward on you. Okay, so equal and opposite forces, we're going to flip the direction and flip the object's position. So the third law force pair for this, you exerting a force down on the floor. And with our normal forces are actually part of this, or they arise because of this third law. It's a reaction force. When you stand on a surface, whether it's a floor or a desk, or you sit on a chair, you're pushing down on that object, the floor, the desk, the chair. As a reaction to that, that surface is pushing back up on you. And that force, that upward force, or that perpendicular force, is a support force that is always going to be equal and opposite to the force that's being exerted down, acting on different objects. And that's one of the important pieces to understand about Newton's third law. The forces are acting on different objects. So the person, you, are exerting a downward force on the floor. The floor is exerting an upward force on you. But it's not always up and down. It doesn't always have to be the floor. Here we have a young man that's leaning against the wall. And so in this case, our force pairs are, and this is the free body diagram dot for the wall. This is the force of the boy on the wall. The force pair to this, the reaction force, is the force of the wall on the boy. Equal in magnitude, opposite in direction, and we see it's perpendicular to the surface. So what happens in this scenario if it didn't push back? Or what happens if you exert a force, or you try to exert a force that is larger than the surface can respond with? So think about a wall of empty cardboard boxes, right? Let's say we build a massive cardboard box fort, and your buddy comes in and they accidentally lean against the boxes. What's going to happen? Did you say it's going to collapse? If you did, you'd be right. The boxes can only exert so much force backward on the person pushing on them. Once that maximum amount of force is reached, the structure, any force greater than that, is going to break apart the structure. And so the cardboard boxes will exert a return force up to a point, and then it will reach a point where the force exerted on them causes them all to fall apart. At that point, it's not going to be a support force. The forces are still going to be the same. If your buddy pushes on the wall of the cardboard box fort with a force of 50 newtons, the cardboard box fort is still going to exert a 50 Newton force back on him, but the reaction to that force is going to be different. It's going to cause the boxes to fall over. It would be the same thing if you started stacking objects up on a table and you kept putting heavy objects on it and it got heavier and heavier and heavier. At some point, the physical characteristics of that table that determine how much upward force it can withstand or it can exert, you're going to reach that limit. And when that limit is reached, the table's going to break and everything's going to come crashing down. Even in the braking, though, those forces are going to be equal and opposite. One other example of this is gravity. And so let's draw another picture here. Here's the Earth. Actually, it's a blue planet, right? So there's the Earth with some land, and some land, and some land. Here's you again, standing on the Earth. Now in this case, if we were to draw a free body diagram of you, we have, again, the gravitational force of the Earth pulling down, the normal force of the surface of the Earth pushing up. These are not force pairs because force pairs act on different objects. So you can't have third law force pairs acting on the same object. So in this case, if the first force is the force of gravity from the Earth pulling down on the person, then the third law force pair then must be the force of gravity on the person pulling up on the Earth. That's right, you heard me. You're exerting a force of gravity on the Earth, and it's the same magnitude as the gravitational force the Earth is exerting on you. Now, what that then means, and we'll talk about this more when we get into the second law, is that not only when you jump off a chair are you falling towards the Earth because it's pulling you down towards it, the Earth is falling upward towards you because you're pulling up on it. Now, we'll talk more about the implications of that later on. Make sure you've taken notes. I'll see you in class.